calculate artillery trajectories for the U.S. Army, and at that time there was no stored program concept. That means you don't handle program as data. Okay, you need to wire to program new problem on this ENIAC digital computer. So there was no programming languages. Also, we need to take a look at the abstractions in computer science and engineering. Computer science and engineering is a science of abstraction. Most of the science disciplines use this notion of abstractions, but especially in computer science, abstraction is very important. And abstraction is the process of considering the external properties of an object. You don't care about the internals, right? You need to build a simple model to solve a complex problem. So by using abstractions, and then you you explore the appropriate solutions to use this simple model. That's abstraction. So if you take a look at the abstraction layers in ENIAC, you see this figure. So at the bottom you have electrons. You abstract the behaviors of electrons using vacuum tubes, right? You use vacuum tubes without considering the behaviors of electrons. That's the merit of using abstractions. So at the bottom, those three layers are in the field of electrical engineering, okay? And above, we have logic gates, right? It's explained by Boolean algebra. And then above that, we have microarchitecture, right? So in this case, we call it hardware, right? Accumulators or flip-flops, and then human being does wiring to program this hardware, okay? And then human being also develop algorithms on top of this hardware, right? There was no concept of software at that time. Very simple, right? Abstractions. But if you take a look at the abstractions in modern computers, you see the layers, very deep layers of abstractions, right? Now you use transistors, not electrons, right? And then you have electronic circuits, logic gates, computer hardware, instruction set architecture, assembly language, high-level programming languages, and algorithm, right? Above these electronic circuits, that's the computer science and engineering area. Now, why the modern computers are so well developed? The reason is that there were holistic optimizations between software and across software and hardware, right? That's the major reason why we have such good digital computers. I'm not comparing digital computers to quantum computers, okay? So, if you take a look at the NISQ systems now, okay? We can compare, it's comparable to ENIAC, the first generation digital computers. There are not that many layers of abstractions. You have at the bottom qubits, and then you have quantum gates, quantum assembly language, and then you have some quantum programming languages, right? And then the quantum compiler does translation from quantum programming languages to quantum assembly language. And then human being developed the algorithms. So there is a big gap actually between physics and computer science. So it's not that easy to bridge the gap because it's very hard to get into each other's field, right? Because of the knowledge, difference of knowledge between them. So you can compare these two approaches, modern computers and current NISQ systems, right? So what we need to do is to bridge the gap, bridging the gap, right? There exists big gap and we need to bridge the gap. But how? I think one of the solutions is virtual quantum execution environments. That means we can have virtual desktop quantum computers on your table. So if we have this virtual desktop quantum computers, right, then the quantum computing will be made practical, right? I don't see the practical result of quantum computers yet. And the user base of quantum computing will be enlarged, and quantum software stacks will be easily developed. For example, quantum operating systems, something like that. And quantum algorithms development will be facilitated, right? I don't see it happens. So, we return to the Professor Praskill's mention. 50 qubits is beyond what can be simulated by brute force using the most powerful existing supercomputers. Now I will rephrase that with this sentence. 50 qubits can be simulated by a high-end desktop or a single rack cluster server based on sophisticated code optimization techniques. Praskill is a physicist, right? He's not a computer engineer or computer scientist, so he doesn't know what is the optimizations. So I know the optimizations. So I can apply the sophisticated optimization techniques to quantum circuit simulation. So this is why I mean the big gap between physics and computer science. Also, we can exploit accelerators. Because of the deep learning in these days, AI technologies, the hardware, the platform hardware have been developed very well, including GPUs, FPGAs, or Google TPUs, or other MPUs, right? You can accelerate your accelerate your computation using these accelerators. And we have heterogeneous computing system equipped with these accelerators. Typically, you run your operating system on general purpose CPUs, and then you run compute-intensive tasks on the accelerators. That's the usage of heterogeneous computing systems. And if you take a look at the trend of top 500, right, or green 500, the supercomputer list in the world. And then you see the heterogeneous computing is computers, supercomputers. The number of heterogeneous supercomputers is increasing. Now it's about 33.6%. Okay? So if you take a look at the trend of supercomputers, you can see the future trend of your desktop servers and your mobile devices. Okay? That's typical. From now, my talk is based on our paper, the SnuQs paper. This is published last year in International Conference on Supercomputing. So I will talk about how to use storage devices to simulate large quantum circuits. So there are two types of quantum circuit simulation method. One is full state simulation and the other is amplitude sampling. So full state simulation is you store full state of your quantum system. So you need a lot of storage spaces, right? And amplitude sampling, you just see not the full state, the part of the state. You see the part of the state when you compute, when you simulate the system. Here, in amplitude sampling, you use tensor network compression method, and full state simulation, we just use Schrödinger equation quantum circuits, okay, to simulate state transitions. And we will focus on full state simulation. And full state simulation is very memory intensive, and amplitude sampling is computing intensive. And using full state simulation, you can do simulation of small but deep circuits very well. For amplitude sampling, you can do large but shallow circuit simulation very well. If you use full state simulation, that's for virtual quantum computers, right? And if you use amplitude sampling, that's for quantum chip validation. For example, if you build a chip, then you can verify or validate its functionality, comparing the result to the simulation result. So, as mentioned before the previous speaker, full state quantum circuit simulation is extremely hard because of the memory capacity. And the classical system requires order of n memory space, but n-qubit quantum system requires order of 2 to the n memory space. So if you take a look at the table below here, as of 2002, Fugaku was the first, the strongest supercomputer in the world, but if you take a look at the memory capacity of the Fugaku, then users can simulate 51 qubits. That's the limitation, okay? So somehow the Prescott was right? He said 50 qubits is the limit of current classical supercomputer. So SnuQs is a simulator, okay? It simulates quantum circuits. It exploits storage devices. For example, hard disks or NVMe SSDs, okay? Solid state disks. So to use this long latency storage devices compared to the DRAM, main memory, we need to manage memory overlays very efficiently, or you need to reduce the I/O overhead of these hard disks or SSD. And this SnuQs, the very cost-effective way of provides very cost-effective way of large-scale quantum circuit simulation. So current limit, I think, if you use your notebook or desktop server, you can maybe simulate up to 34 qubits. You can simulate 100 qubits in your notebook computers, but it takes forever, okay? Because you can use virtual memory implemented in your operating system, but it takes forever, 100 years maybe. So this is overall architecture. You can write quantum circuits in Qiskit or SnuQ, and then you put it into SnuQs, then SnuQs translated the open QSM, and then we optimize quantum circuits, smaller one, make it smaller. And then using this optimized quantum circuits, we do simulation, full state simulation. We have full state simulation library for GPUs and CPUs, and then we have our own runtime system. This runtime system does not use any operating system virtual memory. It just use our own memory overlays, okay, to efficiently handle those storage devices, okay? So here, when we use memory overlays, we use some special amplitude layout design, right? And then we do some qubit computation, okay, to efficiently perform the storage I/O. Okay, that's the key technology, but it's very complicated. So I don't want to introduce it to you here, but you are interested in this technology, then you can read the paper. And then we do automatic sub-circuit partitioning, okay? We transfer the state into the storage device by the unit of sub-circuits. So the bigger, the better. The bigger sub-circuits, the better the simulation speed. And there is a technique called three-step layout transformation, okay? When you use DRAM, main memory, the layout inside the main memory and the layout inside the storage are different. So you need to do transformation somehow, okay? So we developed that three-step layout transformation, and we use bunch of parallelization techniques, GPUs, CPUs, right? And then we build the storage system architecture. for high I/O bandwidth. Bandwidth is very important here, not the latency here. Okay. I just covered it, and we do four types of I/O parallelism, four types of optimizations. I/O parallel. We exploit I/O parallelism. We especially use RAID 0, and we exploit data parallelism. For CPUs, we use OpenMP, and GPUs, we use CUDA. And we do computation and I/O overlapping. And this is very classical optimization techniques in parallel processing. We do overlap computation, CPU, GPU communication, and I/O. So three types of computation can be overlapped here. Also, we do load balancing between subsets. So these four are the techniques we developed for optimizing this simulation of quantum circuits. So to show you the performance of our simulator, we use two benchmarks. Quantum supremacist circuit, it's the factor step out quantum circuit simulation benchmark, and quantum Fourier transformation circuit. Okay? It's very deep circuit somehow, different from quantum supremacist circuit. So this is our storage system architecture. You see the GPUs, right? The red boxes here, 4 GPUs. We use 4 GPUs, and we use 80 hard disks because we need lots of big storage capacity to simulate large quantum system, right? So 80 hard disks. And just one node, okay? 2 CPUs here. So this is somehow very small system, but somehow a larger system compared to your desktop computer because of these hard disks. Okay. Also, instead of using hard disks, HDDs, we can use SSDs. We can use 10 SSDs here, as you see. So we do simulation with this configuration. Here, we use some notation for the circuit name. So if you say QSC-42-50, that means we have 42 qubits, and the depth of the circuit is 50. Okay? So we simulated, the SNQS simulated QSC-4250 within a day. That means about 17 hours. And QFT-4284 within 8 hours. Okay, it takes, a bit long, but it's bearable. Okay, you need to use 4,000 node supercomputer to simulate this. It isn't easily accessible. I don't think so. Instead of that, you just wait a little bit longer. Okay, 10 hours or 17 hours with your one node simulator. If you use NVMe SSDs, 39 qubits, depth 50 takes an hour. Okay, that's QSC. And 78, depth 78, we increase the depth, it's 10 minutes. Sorry, it's not QSC. QFT 3978, in 10 minutes. It takes 10 minutes. Because we didn't have that much money, we could increase the capacity of NVMe SSDs. Now maybe we can, because it's getting cheaper, so we can increase the number of SSDs or its capacity and simulate more qubits, but at that time 39 was the maximum. So about 17 hours of simulation time, and if you compare the cost, if you just use DRAM and if you just use HDDs, using HDDs is about 300 times cheaper than using DRAM. Okay, so it's very cost effective. And if you compare the simulation time with the state-of-art supercomputer. That means, what I mean is that the state-of-art means a supercomputer who simulated, that simulated the biggest quantum system. Okay, so here there is a paper written by Hanner, right? And there they simulated about 47 qubits, but they also reported 42 qubits there. It took about 80 seconds with 4,096 nodes. Okay, but for us, I mean, our SnuQ is just one node. Of course, I mean, it equipped with the 80 hard disks, but it takes 17 hours, right? You just run the simulator and then get out and then have fun and then get back, then you have the result, okay? So that's the comparison. And to wrap up this talk, I just insisted here that there is a big gap between computer science and the physics about the quantum computers. So if we provide virtual quantum computer like SnuQs, then we can facilitate the development of full quantum system. And then SnuQs exploits lots of optimization techniques and new system configuration, and it scales well. Okay, I didn't show the scalability result here, but it scales well. Also, the techniques used in SnuQs can be easily applied to other systems. Okay. We can scale up our node, SnuQs node, then we can simulate a bigger system. So currently we are working on a cluster version of SnuQs. Also, SnuQs is publicly available, so you can download the code using the link shown on this slide. Okay, thank you.
Okay, do you have any questions or comments? Okay. Could you stand up?
Thank you for the seminar. And I have a question that I also saw the GPU on the full stack. So do you think that GPU is not critical, because whole of the seminar, almost of the seminar deals with the memory, not the kind of GPU or CPU. So I'm asking for it.
The problem is they don't know how to use GPUs. That's the problem. If you know how to use GPUs, it's very easy to apply quantum circuit simulation to GPUs. Here, I did not develop new techniques for GPUs. Okay, it's kind of straightforward to fit the quantum circuit simulation to GPU computation. If you are interested in, we will have a summer school at the end of August. You can register.
Thank you for the opportunity.
Other questions or comments?